In this video, we're going to look at some more advanced examples of using the equation method of Hess's law. And this time we're going to be solving for the molar enthalpy of formation of either one of the reactants or one of the products. Our first example is the molar enthalpy of combustion of cyclohexane in a closed system is negative 3,919.6 kilojoules per mole. Determine the molar enthalpy of formation of cyclohexane. So the first thing we're going to do is write a balanced chemical reaction. Cyclohexane has the chemical formula C6H12. And in combustion, it's going to combine with oxygen to form carbon dioxide. And since it's a closed system, we're going to form water as a liquid. So whenever combustion takes place in a closed system, water is going to be a liquid as a product. So we have our reaction. We're now going to balance this reaction. Since we have the molar enthalpy of combustion for 1 mole of cyclohexane, I'm going to leave the coefficient in front of cyclohexane as a 1. This means I might have to use some fractions in front of oxygen. So I have 6 carbons on the reactant side. I need to put 6 in front of carbon dioxide to balance out the carbons. I have 12 hydrogen on my reactant side. So I need to put a 6 in front of the water to balance out my hydrogens. Now I have 12 plus 6, so I have 18 oxygens on my product side, and that means that I need to put a 9 in front of my oxygens here. So I have a balanced reaction. Next, I'm going to look up the molar enthalpies of formation in my booklet. So I know overall this reaction has an enthalpy of negative 3,919.6 kilojoules. And since I'm only reacting 1 mole of cyclohexane, the molar enthalpy is the same as the reaction enthalpy. So we're going to be solving for this value, the formation enthalpy of cyclohexane. The formation enthalpy of oxygen is going to be 0 because it's an element in its standard state. The formation enthalpy of carbon dioxide is negative 393.5 kilojoules per mole. And the formation enthalpy of liquid water is negative 285.8 kilojoules per mole. And these values all come from pages 4 and 5 in the Chemistry 30 data booklet. So we're now going to write down our equation. So our reaction enthalpy is equal to the sum of the coefficients multiplied by the formation enthalpy of our products minus the sum of the coefficient multiplied by the formation enthalpy of our reactants. So we're going to expand on this a little bit now. So our reaction enthalpy is equal to, so our products are carbon dioxide and water. And the only reactant we need to include here is cyclohexane. So we are going to be solving for this variable in our equation, the molar enthalpy of formation of cyclohexane. So we're going to rearrange this equation by basically swapping the locations of our reaction enthalpy and our reactant term. So the number of moles of C6H12 times the molar enthalpy of formation of C6H12 is equal to the sum of our products plus this, so CO2 plus water minus our overall reaction enthalpy. And so to isolate for the formation enthalpy, we're going to divide both sides by the moles of, so the coefficient of cyclohexane. And I'll just delete that from this side. So we've rearranged our equation. So now we can just plug in our numbers. So we have 6 moles of CO2 at negative 393.5 kilojoules per mole. And so we can verify that our moles here will cancel. Plus 6 moles of water at negative 285.8 kilojoules per mole. And then we will subtract our reaction enthalpy, which is negative 3,919.6 kilojoules. And then we're going to divide the entire thing by the coefficient for cyclohexane, which in this case is 1 mole. So it's good practice, even though it's just the number 1, to do that, in case you do end up with a coefficient of more than 1. And we get negative 156.2 kilojoules per mole of cyclohexane as our molar enthalpy of formation. Our next example is the acid catalyzed esterification reaction between methanol and ethanoic acid absorbs 54.2 kilojoules of energy per mole of methanol. Determine the molar enthalpy of formation of the ester. So first thing we need to do is write out the reaction itself. So methanol is CH3OH. Ethanoic acid is CH3COOH. The presence of a catalyst does not change the enthalpy of the reaction, which we'll learn in a later lesson. So when these two react, an esterification reaction creates an ester. So we'll have CH3COOCH3 plus water. And the water will be liquid. So just as a reminder from our organic chemistry lessons, this would be the structure of that ester. And it would be called methyl ethanoate. So we are solving for the enthalpy of formation of methyl ethanoate. We can find all of our other enthalpies of formation in our data booklet. So liquid water is negative 285.8 kilojoules per mole. Ethanoic acid is negative 484.3 kilojoules per mole. And methanol is negative 239.2 kilojoules per mole. And we know that our overall reaction enthalpy is positive 54. So it's positive because we're absorbing energy, so it's an endothermic reaction. And it's positive 54.2 kilojoules per mole of methanol. We have 1 mole of methanol in our reaction. So our reaction enthalpy is 54.2 kilojoules. So we're going to write down our equation. Our reaction enthalpy is the sum of the coefficients times the formation enthalpy of our products minus the sum of the coefficients times the formation enthalpy of our reactants. So to expand on this, our products are, so we have moles of, and I'm just going to write ester just because it's a little bit faster, times delta FH of our ester plus moles of water times the formation enthalpy of water, and then subtract our reactants, so moles of methanol and I'm just going to write acid for our ethanoic acid just to save a little bit of writing. So that's our expanded equation, and we are solving for this value here. So first thing we're going to do is we're going to add this term, so our reactants, we're going to add that to both sides of the equation. We're then going to subtract this term in blue from both sides of the equation. And then lastly, divide the entire thing by the coefficient of the ester. So when rearranged, it's going to look like this. The formation enthalpy of our ester equals our reaction enthalpy plus the enthalpy of formation of our methanol plus the reaction or the enthalpy of formation of our ethanoic acid minus the enthalpy of formation of our water and then the whole thing divided by the coefficient of our ester. So a little bit more complex rearrangement because we can't cancel any terms out. So we're going to fill in our numbers now. So 54.2 kilojoules plus 1 mole of methanol times negative 239.2 kilojoules per mole. And just to check that our units cancel, moles and moles will cancel, so everything will be in kilojoules, plus 1 mole of acetic acid times negative 484.3 kilojoules per mole, and then minus 1 mole of water times negative 285.8 kilojoules per mole, and that whole thing will be divided by 1 mole. So again, even though the 1 doesn't make a difference, it's good practice just to make sure that everything cancels and we end up with the correct units. So our final answer here is negative 383.5 kilojoules per mole.